Welcome to the Chemical Kinetics series of lectures. There will be 5 lectures in this series ranging through a number of topics connected to chemical kinetics. And we're going to start by looking at reaction rates and rate laws. Lecture 1 objectives is to be able to explain what is a reaction rate and why we study rates of reaction. To be able to write an expression that relates reactant or product concentration to reaction rate, to be able to determine the terms in the rate law and measure the rate constant, and to do this, determine the rate law from experimental data. So if we're thinking about kinetics, we are looking at how fast a reaction goes. Our chemical equation, our overall balanced equation, tells us what the reaction is, and thermodynamics will tell us why a reaction actually reacts. So whether it's because, say, it's exothermic or because of some other entropic characteristics of the reaction. But how fast is important. If a reaction goes too slowly, it may be too slow to actually be useful, or if it goes too fast, that could also be a problem. So in pharmacy, we think about kinetics when we look at drug stability, the manufacture of drugs and excipients, and the metabolism of drugs. And in fundamental chemistry, we look at kinetics to tell us how a reaction proceeds. So it tells us what the reaction mechanism is for the chemical equation that we already know. The study of chemical kinetics, we are looking at the rate of change of chemicals during a reaction. And we need to understand how to control the rate of the reaction in order to make a reaction faster or slower, and what are the steps by which a reaction takes place. Here's a few examples of 2 extremes. So here we have the explosion. This is an extremely fast chemical reaction, and it's completely over in a fraction of a second. It's so fast, which leads to that explosive response. Or you can have corrosion on a shipwreck, extremely slow reaction that takes years and years for the build-up of material and the corrosion of the metal or the wood that is within the ship. So these are 2 extremes, but our reactions will also have a rate that will tell us, that will determine some of the parameters of that reaction. We need to think about how we're going to measure the rate of a reaction. So if you have reactants, which we're going to call A, reacting to form products, which we'll call B, then in a reaction, the concentration of the reactants will go down, and at the same rate, the concentration of the products will increase as the reaction proceeds, as you can see in this graph here of concentration against time. The rate of change of reactants can be written mathematically as dA in square brackets over dt. This means the change in concentration of A, the square bracket indicates concentration. So the change of concentration of A against time, the change in time. It is the D that determines that this means changing. Okay. So where we see dA over dt, it is showing us the rate of change in concentration of reactant. And there's a negative sign there because the rate of reaction is equal to the rate of consumption of A. A is being used up in the reaction, so the concentration of A is going down. So it's minus dA by dt. And that will equal the rate of formation of products, which is positive because the concentration of products is increasing during the reaction. So we write this mathematically in this way. dB over dt, meaning rate of change of formation of product. Now the D means change in reactant, and it's the same because it's actually, we use D instead of delta here. It's the same as the triangle that we saw when we're looking at change in enthalpy. Okay, if you see a triangle, it means change in, and if you see a D, it also means change in. So this means change in concentration over change in time. So change in the rate of formation or consumption of reactants or products. As we saw in the thermodynamics lectures, the triangle is important. And so in our rate and our kinetics lectures, the little d, the small d, lowercase d, is also important. It tells us that it's changing concentration over time. The units of reaction rate are therefore concentration over time, which is molar normally as our concentration units, and time can be minutes or seconds. So molar seconds to the -1, which of course we can also write as mole per decimeter cubed per second. In a case where we have two A molecules, so two reactant molecules, forming one product molecule, so 2A going on to form 1B, if you are measuring the rate of this reaction, you need to know that the A molecules will be consumed at twice the rate as the B molecules are formed. So if you're measuring the rate of change of reaction by measuring the rate of change of reactant A, you will need to halve the measured rate to make it equivalent to the rate of formation of B. How do we write that mathematically? Well, we write it as rate equals minus a half dA by dt, which will equal plus dB by dt. So this allows us to equate the rate of formation of the product to the rate of consumption of the reactant. So you can now link the rate of formation of any product in a reaction to the rate of consumption of any of the reactants to take notice of the stoichiometry of your reaction equation. You can now measure the reaction rate by measuring the concentration change of any one of the reactant or products, and you will know how this measurement links to the other constituents within the reaction. A general reaction equation with a small a times the capital A, as you can see at the top here, plus a small b times the capital B. It's just a way of saying reactants where we have a number of reactions of reactant A plus B, the number of reactant capital B, and they go on to form a small c, so a number of the product C and a number of the product D. And you can link the rate of all of these, either reactants or products, by writing out this equation here. So this is a general form for looking at the rate and relating the rate of consumption of those two reactants to formation of those two products based on the stoichiometry of reaction. It's easier to use an example, a simpler example for you to see this working. So how would you write a rate expression in terms of the disappearance of reactants and the formation of products for the reaction where you have two A molecules plus one B molecule going on to form the product C? I'd like you to pause this video and write what you think the rate expression would be using that general formula at the top there for this particular reaction. The rate of the reaction can be measured as the rate of consumption of A or B or the rate of formation of C. But you need to take into account the stoichiometry of the reaction to relate these to each other. So in this case, minus a half dA by dt, so half the rate of consumption of A, is equivalent to the rate of consumption of B, which can also be measured as the rate of formation of C. So it doesn't matter whether in your experiment you're measuring the concentration of A and how it changes with time, or the concentration of B and how it changes with time, or the concentration of C and how it changes with time. You will have a way of linking these together so you can see how it links to the rate of change of any one of those individual elements of the reaction. So here is the first exercise that I would like you to try to do. So I want you to pause the lecture here and try this exercise. The answers are on Blackboard, so I won't tell you the answers during this lecture. So you can do this at any time, but since we've just covered this material now, this would be a good time to have a go. So what is the rate expression in terms of disappearance of reactants and appearance of products for these two reactions? So welcome back. I now want to talk about a specific reaction. So here's a reaction that shows one molecule of bromine forming two bromide ions in this reaction. We can measure the reaction by using a spectroscopic technique that can measure the color change. And as you can see, as this reaction proceeds, it goes from a brown color to a clear liquid. The bromine, the reactant bromine, is colored. So we are measuring the rate of consumption of bromine if we measure the color change. If we are measuring the bromine, we know that the rate of the reaction for what we're actually measuring is minus dBr2 by dt. So the rate of consumption of bromine. There are two ways to think about measuring the rate. First, to measure the initial rate of the reaction. So the rate of reaction at the start of the reaction, where you know the starting concentration of the reactant. So you would measure the rate for multiple different reactions, all with different starting concentrations. And the other option is to measure instantaneous rates, which means you measure concentration at different time points as a single reaction proceeds. And you can then see the instantaneous rate at different points along that curve, where you have measured the concentration of bromine against time by taking the gradient of the curve at every time point and the gradient of that tangent, the curve at each time point, will tell you what the rate of the reaction was at that point in time. So these are instantaneous rates measured from a curve of reactant concentration against time. Here we have a measurement of concentration of penicillin against time, and we can see the rate of change, so that the rate of the reaction can be measured at different time points by measuring this tangent along the curve. So after 5 weeks, the rate is measured from this tangent, which we extrapolate to the axes to allow us to calculate its gradient. And after 10 weeks, the rate of decomposition is slowed, which we can see as the gradient of the tangent is now less steep. So we know we can measure reaction rates by measuring reactants or products and seeing how the concentration of the reactant or the product changes with times. Our rate expressions have shown us this, but we do not know what reactants or other parameters actually determines the reaction rate. We only know how to measure it. To look into how the reactions control the reaction rate, we need to create rate laws. These will be different for each reaction and will not be easily determined from reaction stoichiometry. In this reaction, we have measured the rate of the reaction for different starting concentrations of the two reactants as part of 4 different experiments. From this, it is possible to see how changing the reactant concentration has changed the rate. If we compare the first and the third experiments, the nitric oxide starting concentration hasn't changed, but the oxygen starting concentration has doubled between those two. The rate has also doubled. So this means the rate is proportional to the oxygen concentration. If we compare the first and second experiments, we can see that having twice the starting concentration of nitric acid leads to 4 times the reaction rate. So the rate is proportional to the concentration of nitric oxide squared. So we can say if we double the oxygen concentration, we double the rate. If we double the NO concentration, we quadruple the rate. Finally, if starting the concentration of both reactants is doubled, so let's compare the first and the fourth reaction, then the rate becomes 8 times. You can see the rate of the fourth reaction is 8 times the rate of the first reaction. And this is the combination of the 2 times from doubling of the oxygen and the 4 times from doubling of the nitric oxide. And we see this comparing these first and the fourth reactions. This means the rate is proportional to the nitric oxide concentration squared times the oxygen concentration. So we say that the reaction rate is first order with respect to oxygen, second order with respect to nitric oxide, and it is third order overall. So that is the N plus the M gives you the overall order of the reaction. So from this we can see that the rate is proportional to the concentration of the nitric oxide squared times the concentration of the oxygen. If you replace the proportionality sign, we can say the rate equals the concentrations to the power of their orders multiplied by a constant. So remember, we have worked out the orders from the experiment. So we've now replaced that proportionality sign, and so we have now introduced a constant known as the rate constant. So our rate law is that the rate equals K times the concentration of nitric oxide squared times the concentration of oxygen. The rate law is an expression that relates reactant concentrations to the reaction rate. And it's the reactant concentrations that's going to be the things that determine the rate of the reaction. And the rate law shows us how. So a general way to write the rate law would be to use this example here. For a reaction of A and B forming products, the rate will depend on the concentrations of the reactants as determined by the rate law. The rate will equal K times the concentrations of A and B to the power of N and M, where N and M are the order of the reaction with respect to these reactants, as we saw in our example. Remember, we cannot guess N and M from the stoichiometry of the overall balanced reaction equation. The only way to find N and M is by experiment, as we have seen in our example. Going back to our example, we have found that the rate equals K, the rate constant multiplied by nitric oxide concentration squared times the oxygen concentration, and we can use one set of experimental data to work out the value of the rate constant. You can calculate K using any of the experiments. In this case, the units of the rate constant is molar to the -2, seconds to the -1. If the overall reaction was first or second order, the rate constant would have different units because the equation would be different. That is, we have set up here to determine the rate constant. So here is an example for you to look through of determining the rate constant from that experimental set of data. Let us try another example. I'd like you to pause the video and try to answer this question. This is the end of this lecture, so you'll be able to go to the summary slide or the next slide and then have a go answering this question. Again, the answer will be provided on Blackboard. We have covered a lot of content in this first lecture. Make sure you can do both the exercises from the lecture and look through the answers on Blackboard. You can use the Padlet that is situated to the left-hand bar of the Blackboard site and is called R Green Lectures Padlet to ask me questions anonymously. We will also have a summary live online lecture next week to go through key concepts.